Okay. Hey, folks. So let me try and adjust this. There's a lot of lights to make this green screen happen. Uh, okay. So you may have heard from me in a slightly different shirt earlier this morning for my time that I was going to skip the variance sum laws. Well, I decided not to skip them. Just so that those of folks who are on the stats side of this class have that little bit of peace to like know why we can essentially partition variance. It's pretty neat. Um so let's dive in. Variance sum laws. So the variance sum laws, law singular, is essentially allows us to create composite score by combining multiple items. And the cool thing is that the variance of the composite is a combination of the variances and covariances of the individual items within it. So if you know the components of the score, you can figure out what the composite's uh, variance is. So that's essentially how we can calculate the proportion of variance of true score and total score. And break up total score into true score and error. Sorry, I misspoke. So here's the basic law. It's not really a law, it's a proof. But if x and y are random variables, which they are for like all our tests, then the covariance of x plus y is the sum of the variances of x with y plus or minus the 2 times the covariance of the individual item, which is pretty neat. And the reason why we can do all the classical test theory stuff and all the reliability calculations is because we make a simple assumption that can be a little problematic in reality. But the assumption is that our two components, the true score, here x, and our error, are unrelated to each other. That's why the error is random. Because then we don't have to worry about true score and error correlating. Because we told it that it never happens. While in reality, it does happen, and it violates a lot of statistical theory because of that assumption being, well, violated. But from a simplification standpoint, it's pretty awesome. So let me illustrate. If we are just looking at 3 variables, here x1, x2, and x3, we can create a really basic variance covariance matrix, which is it's like a correlation matrix where you show all the relationships, but it's not standardized. And what that means is on the diagonals is just the variance for our two. So the covariance of x with y is the variance, while the covariance of x1 with x2 is that. And all right, sorry I'm babbling. So this is the data shape we're working with, and when we have actual data here, the covariance of x with y is 29 and a smidge, while the covariance of x with z is 30, etc. So to find out what the composite is of this variance, all we need to do is add them up plus double their variance matrix covariance. So the plus or minus is, I guess I'll back up. So the plus or minus really just depends on if they're positively or negatively associated. So if they're positively associated, you add them. And for us, for all intents and purposes, we can just add them. So here, to find out what the covariance is of our total score, we can just add up the pieces and just plop them right into our model here, which would give us 254 by adding up the covariance or the variances of the three. So 55, 17, and 23, 29. I'm sorry, I cannot read words that are numbers out loud. There's some horrible disconnect in my brain. But that's enough about me. And then we just add up the covariances between those items to get our total variance of our composite. That's it. So that's why all the simplifying assumptions that we have in classical test theory exist. Because we want to be able to do really easy variance sum laws. Because then you just add them. That's it. That's how we can get that total score and the ratios without having to like find out what the covariance is and all that other stuff. It's great. So that's the variance sum law. It's a neat thing. I like it. And I use it a lot in my work. Ooh, I cannot read. I apologize. Let me back up and actually we'll cut it here. That was convenient.